Welcome to Module 1 of our course on well logging and interpretation. In this first module, we will build a solid foundation by exploring the principles, tools, and processes that form the backbone of well logging. Think of this as the what, why, and how of well logging before we move into more advanced interpretation techniques in Module 2. Our journey will start with the history of well logging, then move through the different types of logs, the physics behind them, the environment in which they are taken, and finally, how data is acquired and quality controlled in the field. 1. Introduction to well logging. Well logging is the process of making detailed records, or logs, of the geologic formations penetrated by a borehole. These logs are essentially a continuous record of the physical, chemical, and sometimes acoustic properties of the rocks and fluids encountered during drilling. The main objective of well logging is to gather subsurface information without having to extract large rock samples. Instead, specialized tools are lowered into the borehole to measure properties such as resistivity, natural radioactivity, density, porosity, and acoustic velocity. Well logging plays a pivotal role in the petroleum industry, as it helps geoscientists and engineers make informed decisions about where hydrocarbons might be located, how much is there, and how best to produce them. It's also used in groundwater exploration, mining, and geotechnical investigations. 2. Historical development of well logging. The concept of well logging began in 1927, when the Schlumberger brothers performed the first electrical log in France. This early method measured the resistivity of formations, giving an indirect clue about their fluid content. Over the decades, technology evolved from simple resistivity tools to a sophisticated suite of sensors capable of measuring multiple parameters simultaneously. The development of nuclear logging tools, sonic logging, and borehole imaging has revolutionized our ability to see into the rock without physically retrieving it. 3. Types of well logs. Well logs can be broadly categorized in several ways. By borehole condition. Open hole logging is performed before the well is cased and cemented, giving direct readings of the formations. Cased hole logging is done after casing, mainly for monitoring and production purposes. By method of deployment. Wireline logging involves lowering tools into the borehole on a cable to record measurements continuously. Logging while drilling, LWD, and measurement while drilling, MWD, gather data in real time during the drilling process, reducing the need for separate logging runs. 4. Basic principles of log measurements. Well logging tools measure physical properties that correlate with lithology and fluid content. Electrical resistivity differentiates between water-bearing and hydrocarbon-bearing formations. Natural gamma radiation indicates shale content. Density helps determine rock type and porosity. Neutron porosity estimates hydrogen content, which often correlates with fluid field porosity. Sonic velocity used to derive porosity and mechanical properties. The key is understanding that each measurement reflects a combination of factors. For example, resistivity is influenced by both porosity and the type of fluid in the pores. 5. Drilling and logging environment. The borehole environment plays a huge role in the accuracy of logs. Factors such as drilling mud type, borehole diameter, rugosity, roughness, and temperature can significantly affect tool readings. Drilling mud is particularly important because it can invade the formation, replacing formation fluids near the borehole wall. This mud filtrate invasion changes the log response, especially for resistivity measurements. 6. Common logging tools and technologies. Let's take a closer look at the main categories of logging tools. Resistivity tools measure how strongly the formation resists the flow of electrical current. Hydrocarbons are poor conductors, so resistivity tends to be high in oil or gas zones. Density tools emit gamma rays into the formation and detect how many are scattered back. Denser rocks scatter more gamma rays. Neutron porosity tools detect hydrogen atoms, which are abundant in water and hydrocarbons. Sonic tools send acoustic waves through the formation and measure travel time, which is related to porosity and rock type. Gamma ray tools measure natural radioactivity to distinguish shale from non-shale rocks. 7. Borehole corrections and environmental effects. Every logging tool has limitations, and raw data must be corrected for environmental effects. These corrections may account for borehole size variations, temperature and pressure differences, mud cake buildup, Tool standoff from the borehole wall. Environmental corrections are essential for ensuring that the logs represent the true formation properties, not artifacts caused by the borehole environment. 8. Data acquisition process. The process of logging begins with careful planning, choosing which tools to run, in what order, and at what depths. During data acquisition, tools are calibrated before entering the hole. Measurements are recorded continuously as the tools are pulled up the well. The data is transmitted to surface systems for real-time monitoring. Quality control checks are performed immediately to ensure accuracy. If problems are detected, such as noisy data, tool malfunction, or unexpected borehole conditions, corrective actions can be taken on the spot.